There's a refrigerant sitting in the back of every cold storage warehouse in this country right now that can make ice from nothing but heat and gravity. Not a synthetic, not a patent. Ammonia, a compound so simple it is 3 hydrogen atoms bonded to 1 nitrogen. It was making ice in American homes before your great-grandparents were born. It required no compressor, no electricity, no moving parts. A flame the size of a candle wick was enough to drive the entire cycle. And by 1941, over 2 million American homes had a refrigerator that ran on exactly this chemistry. Then it was taken from you. Not because it failed, because it could not be monopolized. Let's trace it back. In France in 1859, a mechanical engineer named Ferdinand Carré filed a patent for the first ammonia water absorption refrigeration system. The principle was elegant and required almost no engineering sophistication to understand. Heat ammonia water in a sealed vessel. The ammonia boils off, first, because its boiling point is far lower than water. Route the ammonia gas through a condenser where it liquefies. Let that liquid ammonia evaporate in a separate chamber. As it evaporates, it absorbs enormous amounts of heat from its surroundings. The air around it goes cold enough to freeze water into solid ice. Then the ammonia vapor returns to the water, reabsorbs, and the cycle resets itself with the application of heat. No compressor, no piston, no motor. Nothing moves except molecules. The energy source is heat itself, a wood fire, a gas flame, sunlight concentrated through a lens. Anything that generates warmth can drive ammonia refrigeration. Carré proved this was not theory. He built a machine that produced 200 pounds of ice per hour using nothing but ammonia, water, and a wood-fired boiler. When the American Civil War disrupted the shipment of natural ice from New England to the southern states, Carré machines were brought into New Orleans and other Confederate cities to fill the gap. Hospitals that had depended on northern ice to cool fever patients now produced their own. A French absorption system running on firewood was keeping wounded soldiers alive, while the rivers of New England sat unharvested above the Mason-Dixon line. To understand what ammonia replaced, you have to understand what came before it. And what came before it was an industry so large, so embedded in the American economy, that its collapse reshaped the country. Before mechanical refrigeration existed, America ran on harvested ice. Workers cut blocks from frozen lakes and rivers every winter, packed them in sawdust, stored them in massive ice houses, and shipped them across the world. A Boston entrepreneur named Frederick Tudor, who history remembers as the Ice King, started the trade in 1806 by shipping New England ice to the Caribbean. Within decades, he was sending ice by sailing ship to Calcutta, Bombay, and Madras. Tudor's India shipments alone generated over $220,000 in profit between 1833 and 1850. In today's money, that is nearly $5 million from selling frozen water to the other side of the planet. By the end of the 19th century, the American ice trade employed an estimated 90,000 people and 25,000 horses, operating in an industry capitalized at $28 million, roughly $660 million in today's terms. Ice was the second largest American export behind cotton. 20 million tons of it sat in warehouses at any given time. Entire railroad systems were built around moving it, and then ammonia killed it, not with a single blow. With a slow, quiet thermodynamic inevitability, because ammonia could make ice anywhere, anytime, regardless of weather, regardless of geography, regardless of whether winter came at all. A factory in South Texas, running a Carré absorption system in the 1880s, was producing 1,000 pounds of ice a day, fired by nothing but wood. No frozen lake required, no 90,000-man labor force, no fleet of ships, just chemistry. By the early 1900s, ammonia-driven mechanical refrigeration was the standard for commercial ice production, breweries, meatpacking plants, and cold storage warehouses across America. Carl von Linde, a German engineer, had filed his patent for a compressed ammonia refrigeration system in 1876 and sold it first to the Bavarian brewing industry. Linde machines spread across Europe and then to America. The natural ice trade, which had shaped global shipping routes and employed small cities of workers, collapsed within a generation. By 1914, American factories were producing 26 million tons of artificial ice per year, exceeding the 24 million tons of naturally harvested ice for the first time. By the end of World War I, the natural ice industry was functionally dead. Ammonia had won. It was cheaper, it was reliable, it worked in any climate, and it was about to enter your home. In the 1920s, domestic refrigerators using ammonia absorption systems began appearing in American kitchens. These machines had no compressor and no electric motor. They ran on a small gas flame, usually natural gas or propane. The ammonia circulated in a permanently sealed system with no moving parts. A company called Serval manufactured the most successful version. By 1941, Serval had sold over 2 million gas-powered ammonia refrigerators to American households. They were quiet, reliable, and required no electricity whatsoever. In rural America, where electrification was still decades away for many families, a Serval ammonia refrigerator was the only way to keep food cold. Many ran continuously for 30, 40, even 60 years without a single repair. And then Albert Einstein got involved. In the 1920s, newspapers in Berlin reported a family killed in their sleep by toxic fumes leaking from their refrigerator. The refrigerant in that unit was not ammonia. It was methyl chloride, a colorless, odorless gas that early home refrigerators used because it worked in smaller compressor systems. Methyl chloride was lethal at concentrations that the human nose could not detect. The seals on these early compressor units failed regularly. People died. Einstein read the newspaper story and was disturbed by it. Working with his former student Leo Szilard, he spent the years between 1926 and 1934 designing a refrigerator that could never leak. Because it had no moving parts and no mechanical seals to fail, their design used ammonia, water, and butane in a sealed absorption cycle operating at constant pressure. Einstein and Szilard were granted 45 patents in 6 countries for 3 different models. The design was safe, silent, and required nothing but a heat source to operate. It was the serval concept refined to its most elegant form. It was never commercially produced. Here is why. In July 1929, a New York Times headline read, "Ice machine gas kills 15 in Chicago." The deaths were caused by methyl chloride leaking from commercial and residential refrigeration units, not ammonia, methyl chloride. But the public panic that followed did not distinguish between refrigerants. The entire concept of chemical refrigeration in the home became suspect. People in some neighborhoods began moving their refrigerators to their back porches and backyards. 3 corporations saw an opportunity in that panic. General Motors, DuPont, and Frigidaire had been collaborating since the mid-1920s to find a new refrigerant. Their lead researcher was a mechanical engineer from Dayton, Ohio, named Thomas Migley Jr. In 1928, Migley and his colleague Albert Henna synthesized dichlorodifluoromethane, the first chlorofluorocarbon. DuPont trademarked it as Freon. In 1930, Migley stood before the American Chemical Society, inhaled a lungful of Freon gas, and exhaled it onto a lit candle extinguishing the flame. The demonstration was designed to prove 2 things simultaneously. Freon was not toxic. Freon was not flammable. The audience applauded. The press covered it widely. Within months, General Motors and DuPont formed the Kinetic Chemical Company to produce Freon at industrial scale. By 1935, Frigidaire and its competitors had sold 8 million refrigerators in the United States using Freon as the refrigerant. 8 million units in 5 years. An entire national infrastructure of dealers, installers, and service technicians was built around the compressor refrigerator running on a patented synthetic gas. Ammonia absorption refrigerators, which needed no electricity, no compressor, no service contract, and no patented refrigerant, were systematically pushed out of the market. The Serval Company, which had dominated rural America with its gas-powered ammonia units, went out of business in 1957. Consumers were embracing the all-electric kitchen. General Electric, Westinghouse, and hundreds of utility companies had launched the Live Better Electrically campaign, complete with gold medallion certifications for homes that ran entirely on electricity. The message was everywhere. Modern meant plugged in, efficient meant motorized, cold meant compressor. Ammonia did not fail, it was outsold by a product backed by 3 of the largest corporations in American history, supported by a national marketing apparatus that redefined what a kitchen was supposed to look like. Now here is the part that should make you reconsider every appliance in your house. Thomas Migley Jr., the man who invented Freon, had previously invented tetraethyl lead, the additive that put lead in gasoline. He knew lead was toxic. He contracted lead poisoning from his own work and had to take a medical leave. He held a press conference in 1924 where he poured tetraethyl lead over his hands and inhaled its fumes to prove it was safe. He was lying. Workers at his production facilities were dying. Others suffered hallucinations and went insane. The plant was shut down by the state of New Jersey. When Migley turned his attention to refrigerants, he produced a compound that solved the immediate problem of toxicity and flammability in the kitchen. But Freon, and the class of chlorofluorocarbons it spawned, accumulated in the upper atmosphere and began destroying the ozone layer. The ozone layer that protects all life on Earth from ultraviolet radiation. Environmental historian J.R. McNeil wrote that Migley had more adverse impact on the atmosphere than any other single organism in Earth's history. Bill Bryson described him as possessing an instinct for the regrettable that was almost uncanny. In 1987, the Montreal Protocol banned chlorofluorocarbons worldwide. The replacement chemicals, hydrofluorocarbons, solved the ozone problem but created a new one. HFCs are potent greenhouse gases, thousands of times more effective at trapping heat than carbon dioxide. They are now being phased down under the Kigali Amendment to the Montreal Protocol. And through all of this, through the ozone crisis, through the greenhouse gas crisis, through 2 generations of synthetic refrigerants that each turned out to be worse than the last. Ammonia sat quietly in every industrial cold storage facility in the country, doing exactly what it had always done. Ammonia's ozone depletion potential is 0. Its global warming potential is 0. The International Institute of Ammonia Refrigeration publishes data showing that ammonia is 3 to 10% more thermodynamically efficient than any competing synthetic refrigerant. A system running on ammonia uses less electricity to produce the same cooling output. The cost of ammonia as a refrigerant is measured in dollars per pound. The cost of synthetic alternatives is measured in tens of dollars per pound, often rising higher during supply disruptions and regulatory transitions. Ammonia refrigeration provides air conditioning for the International Space Station. It cools the systems of Biosphere 2. It is the backbone of every cold storage warehouse, every meatpacking plant, every dairy processing facility in North America. Practically every piece of food you eat passes through at least one ammonia refrigeration system before it reaches your grocery store. The industry that feeds the country runs on ammonia. You are simply not allowed to use it in your own kitchen. The stated reason is safety. Ammonia is toxic at high concentrations. Exposure at 300 parts per million is immediately dangerous to life and health. A major leak in a confined residential space could be lethal. These are real hazards. They are not invented, but they require context. Methyl chloride, the gas that killed families in their sleep in the 1920s, was odorless. You could not detect it before it killed you. Ammonia has one of the most distinctive and pungent smells of any chemical compound on Earth. A leak of even a few parts per million is immediately detectable by the human nose. You smell it, and you leave the room. The self-warning property of ammonia is one of the reasons it has been used safely in industrial settings for over 160 years. The safety record, in context, is not a failure of ammonia. It is a failure of engineering applied to the wrong refrigerants. The Einstein Sealard refrigerator solved the engineering problem. A permanently sealed system with no moving parts cannot leak at a mechanical seal because it has no mechanical seal. The design was proven, the patents were filed. Oxford University revived the concept in 2008 and reported the potential to quadruple the efficiency of the original design. It has still not been commercially produced. Follow the money, and the pattern repeats. A compressor refrigerator has a motor that wears out. It has a compressor that fails. It has a refrigerant that must be recharged. It has a service contract. It has a replacement cycle of 10 to 15 years. Every unit sold creates a downstream revenue stream of maintenance, repair, and eventual replacement. The average residential cooling customer is worth thousands of dollars across a system's lifetime. An ammonia absorption refrigerator has no moving parts. It requires no electricity. Its sealed system can operate for decades without service. Its refrigerant costs pennies and cannot be patented. The serval units that survive today, some of them 80 years old, still work. There is no service revenue. There is no replacement cycle. There is no recurring relationship between manufacturer and customer. A product that works indefinitely and never needs you to come back is not a business model. It is a threat to a business model. The knowledge was never lost. It was simply not handed to you. Ammonia absorption refrigerators are still manufactured today. They are used in recreational vehicles, off-grid cabins, and remote medical facilities across the developing world. They run on propane, natural gas, kerosene, or any heat source capable of reaching the temperatures needed to drive the absorption cycle. A flame the size of a candle wick is sufficient. If you live off-grid or in an area with unreliable electricity, absorption units are available from specialty manufacturers and ship direct. They produce no noise. They require no generator. They keep food frozen in environments where a conventional refrigerator would be useless. But the broader question is not about off-grid living. The broader question is why, in an era of climate crisis, when synthetic refrigerants are being banned one by one for destroying either the ozone layer or the climate, the original refrigerant, the one with zero ozone depletion, zero global warming potential, 3 to 10% better thermodynamic efficiency, and 160 years of industrial service record, is still excluded from the one market where it could do the most good: your home. The ice trade employed 90,000 people. Ammonia ended it in a generation. The ammonia refrigerator served 2 million American homes. Freon ended it in a decade. Freon tore a hole in the ozone layer. The Montreal Protocol ended it. Its replacements are now accelerating climate change. The Kigali Amendment is ending them. Every synthetic refrigerant introduced to replace ammonia has eventually been banned for the damage it caused. Every one. The original compound, the one that has never been banned, that has never damaged the atmosphere, that has never required a regulatory phase down, still sits in the warehouse cooling your food before it reaches you. Ferdinand Carré built the first ammonia ice machine in 1859. It made 200 pounds of ice per hour from wood-fired heat. Albert Einstein and Leo Szilard designed an ammonia refrigerator in 1926 that had no moving parts and could never leak. Serval sold 2 million ammonia refrigerators to American families by 1941. The International Space Station runs on ammonia cooling right now, orbiting above a country that will not put the same chemistry in a kitchen. Ammonia's chemical formula is NH3, 3 hydrogen atoms, 1 nitrogen atom. It occurs naturally in the environment. It breaks down into hydrogen and nitrogen, two gases that make up almost the entirety of the air you're breathing. It cannot be patented. It cannot be branded. It cannot be monetized in the way a synthetic molecule owned by a chemical conglomerate can. And that is why you have never made ice with it. So drop your setup in the comments. Do you run on grid or off? Do you have propane access? Do you live in a region where the power goes out and your food rots while the utility company issues a timeline? Because the answer to all of that has been sitting in a sealed tube since 1859, waiting for you to find it. And if you believe real knowledge keeps getting buried to protect someone's quarterly earnings, hit subscribe. Because next week, I'm covering the ventilation design Victorian engineers used to cool entire hospitals, documented by the Royal Institute in 1869, and why modern building codes made it illegal